As I told you yesterday, the entire talk yesterday was in some sense a preparation for what is going to happen today. So, today I want to talk about cosmological constant. So, I will start with a somewhat closer look as historically how we have attempted to attack this problem. Then I will try to convince you that the real problem with the cosmological constant is somewhat different, and then I will provide a solution to that, which involves one definition, which is okay, but I will make a postulate about that definition, and out of that I will get you the value of the cosmological constant. Now, obviously definition is not an issue, and this is just math. So, it is everything is hidden in this postulate, and why that postulate should be true. That part is speculative, but it leads to a new perspective on cosmology, which depending on how much time I get, I will try to elaborate on. Okay, so, the first point which I tried to convince you yesterday is that our universe, when you describe it properly in terms of genuine constants, is rather strange. It has three phases: the inflationary phase, then the sort of radiation and matter phase, and it has the late time acceleration phase. And in the current thinking, there is absolutely no relation to each other. Each of these are characterized by an energy density. In the inflationary phase, you have the rho inflation, and then radiation matter density phase is decided by rho eq, and the late time acceleration is decided by rho lambda. And there is absolutely no relationship in conventional cosmology between these three numbers. So, this is the graphical picture which we will keep coming back to. So, what is plotted here is the Hubble radius of the universe as a function of epoch. So, during the inflationary phase it is sort of constant, and then it sort of goes over to a radiation dominated phase and then a matter dominated phase, and here in the cosmological constant dominated phase it again goes to flat. So, the universe is essentially making a transition between two de Sitter phases through some matter and radiation in between. In principle, these two can go to eternity. So, if you do equal weightage in time, this is completely transient. So, you have these three energy densities, and as I explained to you, we do not really worry about rho inflation, because we believe some high energy physics theory will give you what it is. We also do not worry too much about rho eq, because we again think that high energy physics will fix that. So, the real problem in some sense, which has attracted a lot of attention, is that we have no clue whatsoever as to why this number is so tiny. Okay, so, this is the question. Now, let us take a closer look at that. First of all, if you consider pure gravity, matter free gravity, then that can be described by r and lambda. So, the constants which are involved are g, c and lambda, and you can easily convince yourself that there is no dimensionless number which you can build out of g, c and lambda. Okay. So, in pure gravity in classical setting, no h cross, there is no fine tuning problem, because you can't create a dimensionless number and say it is small. Now, let us go and add matter, classical matter with classical gravity. Let us not bring in h cross anywhere yet, or Planck length anywhere yet. Then I told you yesterday that the evolution equation of the post inflationary universe is very simple. This x here is a by a eq, and I have introduced a dimensionless time scaled with respect to the h lambda later on. Then the dynamics is entirely determined by one dimensionless parameter, which is the ratio between the rho lambda to rho eq, and that number is like 10 to the minus 10. So, this is what I mentioned yesterday, that these two scales have a difference 10 to the minus, in terms of Planck length, one was 113 and the other was 123. So, they differ by a factor 10 to the 10. So, you may take the point of view that this is rather a small number, and you can ask why classical cosmology, which is very well determined now observationally, is decided by two densities with a dimensionless ratio which is like 10 to the minus 10. It is not 120, but it is still a small number, and you can ask the question, and we have no answer to that. We do not know where it comes from, because it involves rho lambda, and even if you fix rho eq, until you know rho lambda, you cannot answer this. So, this is, so to speak, the classical cosmological constant problem. But of course, people, as I said, the other reason why people worry about the 10 to the minus 123 is because one believes that lambda has something to do with quantum theory. So, let me go over it a little bit, especially for those in the audience who do not do this sort of thing. So, as I said, the standard view is that rho eq, which is being 113, is fine, but this is a problem. Okay. And I explained to you why we take that point of view. And there is this view that cosmological constant has something to do with quantum theory. So, what does it have to do? First, there is this very prevalent wrong calculation. I want to take a moment and possibly set the ghost to rest. So many popular and not so popular books will calculate the 0 point energy half h cross omega of a system, integrate it over k, and you will put a cutoff at some k max to the power 4 or 1 upon L max to the power 4, and you typically take L max to be like Planck length, and you say, oh my God, I mean this is giving you a value which is very large. Now, this anyone who has done quantum field theory will tell you that this calculation is meaningless. Okay. So, there is very rigorous way of regularizing divergence integrals in quantum field theory, and if you do that properly, this will just go away. And in fact, you cannot get the correct pressure if you do it like this. So, cosmological constant problem is a problem about P and rho being related to rho is equal to minus P, and you will not get it here. But if you do it properly, like if you use, for example, dimensional regularization, then you will get this result. For example, if you are thinking of a scalar field with these modes and you do that scalar field correctly, and if the field has a mass m, then this is the kind of thing you will get, and there is a regularization scale or a renormalization scale which will come up there. And this will indeed tell you that if you have a bare cosmological constant, then the effective cosmological constant, like any other coupling constant in quantum field theory, will run with energy, and it is this energy scale which you have, and then you can play games with that. This is interesting, and this probably means something, but there is a much more serious problem with cosmological constant. This was actually emphasized by John Barrow in his first talk. The point is, this is what field theoreticians would call a fluctuation calculation or a loop calculation. But even at tree level, we know that the universe went through several phase transitions. At that time, at tree level, the potentials in the universe changes by a fairly large number, and the cosmological constant should pick up in the conventional theory even at the tree level from the Higgs potential or at various other phase transitions. So, you do have a issue that this level keeps changing, and finally, it somehow magically arranges itself to have a very tiny value compared to very large values. So, this has been known, and the problem has been solved several times in the literature. My fond hope is that I will be the last guy to solve that problem. Everything works at some level, and there are assumptions in it, and everything does not work at some level, but I will just run through that. If your favorite solution does not apply, does not appear there, I am sorry about it. So, the simplest solution is just accepted, it is just a number, okay, and that is the number the universe is made of. Lambda LP square happens to be 10 to the minus 122, and be done with it. Obviously, this is not a solution, and again, as I told you, at tree level, if the universe is changing through its 0 point energy and it is not being picked up, something is actually wrong. So, I do not think this is a solution at all. There has been ideas based on what you call Le Chatelier's principle or the dynamical relaxation. So, the idea is that suppose you have a region which has a lambda, then you look at the dynamics, gravitational dynamics there, and if you put quantum field theory there, will it be possible that the quantum field theory has an expectation value of the stress tensor energy, which sort of goes in with a sign which is opposite to what is lambda producing, so that it will sort of balance each other and it will relax back to effectively 0 value. It is a very attractive idea because it is a self-consistent way of killing lambda, but it does not work. Okay. People have tried it, but it does not work. The other favorite exercise, which I keep getting papers to referee, is to make rho lambda a function of Hubble parameter. So, it evolves with time, and you can then arrange things in such a way that it has the correct value there and it had a different value earlier on, and it goes on. More often than not, this is done inconsistently, not philosophically, purely algebraically inconsistently. That has been again alluded to several times in the literature, because there is an integrability condition to Einstein's equation, which is encoded in Bianchi identity. So, if you just go and change the density and you do not change the pressure, or you do not change the coupling between matter and these terms, then you are actually doing wrong mathematics. Okay. But even if you do it correctly, it requires some ad hoc assumption as to how it is happening. One idea which I am rather fond of, not so much because it works, but because it came much before the cosmological constant was discovered. This came from Raphael Sorkin, and he was at that time pushing a particular approach to quantum gravity based on causal sets. And he pointed out that in the causal set approach, there is a relationship between cosmological constant and the current Hubble constant, and it is at the right ballpark figure. Okay. It comes from some kind of stochastic fluctuations. Many people have worked on it, including me, John Barrow, various people. And one way of looking at this, which I find rather attractive, is that if you have a quantum field theory and you look at the Hamiltonian operator of the quantum field theory, it is a spatial integral over a Hamiltonian density. So, the vacuum state is an eigenstate of the total Hamiltonian operator, but if you just take a spherical region of some volume and then you compute the Hamiltonian inside that volume, that is not the total Hamiltonian. So, the vacuum state is not an eigenstate of that Hamiltonian. Therefore, there will be energy fluctuation inside that volume, and you can take that energy fluctuation and divide by the volume on which you are computing, and you can calculate how much it contributes. It turns out that you can arrange matters in such a way that that gives you the right level, and in this case the lambda will be a stochastically fluctuating variable, and you should be writing down Friedmann equations as some kind of a stochastic differential equation, and you integrate it, etc. If observations come and tell you that about 1 Hubble time earlier lambda sign sort of flipped, then this would be back in vogue, but until that happens, it is not probably a good way to go about solving this, but it is an interesting one. Another approach is to go and find a symmetry, which will be the symmetry of gravity if lambda is equal to 0, but if lambda is non-zero, that symmetry should be broken. In that case, you can say that the lambda is strictly 0 because of this symmetry, and all symmetries in nature probably are broken at some level, and that is what leads to this tiny value of the cosmological constant. All kinds of symmetries has been introduced for this. Probably the most non-conservative one was from Tooft, who said that what about changing every coordinate into I times that coordinate, and you can show that sort of, if lambda is 0, it is still a symmetry, but not otherwise. Other possibility is to say that there should be a symmetry between E and minus E, where E is the energy of a system. This you can do by taking an R root minus E and a minus R root minus E and balancing things out. And of course, the classic example is supersymmetry, which will give you some kind of lambda equals 0, but we know that it is broken. So, if you can find a symmetry and a weak reason for breaking that symmetry, then you can do that. Another class of ideas is to introduce either non-local or acausal actions. I mean, it has been noticed for a very long time, and I could never find the earliest historical reference. If some of you know, you should tell me. I learned it from my supervisor, that you can think of lambda as a Lagrange multiplier for the total 4 volume of the universe. Okay. So, you say that you are only going to vary things keeping the 4 volume constant, and then you can bootstrap it back, and you can write down an action principle which involves integration in time all the way to infinity and integration in space all over the region, and then try to ask what the value of lambda is. It does again work, but you pay a price for that. There is a rather attractive idea which Grisha Wolovic has been pushing, and he has an entire book. I think it's titled some Universe in a Helium Atom. And the idea is actually quite clear in the condensed matter context, but whether you can use it in cosmology is the place where all the ifs and buts come in. So, there are systems in condensed matter where the relevant quantity which you should look at is not the Hamiltonian, but Hamiltonian minus mu times n in grand canonical ensemble, where n mu is the chemical potential and n is the number of particles. And if you look at its density and you calculate its thermal average, this will essentially go as energy density minus mu times the number density, but there is a Gibbs-Duhem generation which tells you that that is equal to minus P plus Ts. So, if this is the relevant quantity to look at, then that energy is minus P at 0 temperature state. So, you get the equation of state for cosmological constant free, and then you have to build a model around it as to there are some kind of modes which are sub-horizon, some modes which are super-horizon, and there is an interplay between them. And that part has always been a bit of a problem, but in condensed matter context, this is a very well established principle. Then there is an idea called unimodular theory, and I am going to push something which is very similar to that. So, I will talk about it later on in that context. So, this is the situation. So, we have a whole lot of solutions to the cosmological constant problem. My personal take is essentially what Chesterton has said in a different context. So, what really is the problem with lambda? I introduced lambda in a particular way yesterday in order to motivate this. If you add a constant to the standard model Lagrangian or any matter Lagrangian you have, it keeps the equations of motion of matter invariant. But the gravitational field equations, once you couple this to gravity, then if you add a constant, you can prove fairly simply, it is a theorem, but it is a two-step proof, that gravitational field equations cannot remain invariant under an addition of a constant, any gravitational Lagrangian, it does not matter how you modify gravity. If the theory is generally covariant and built on a local action, and the metric is varied unrestricted, that you do not do unimodular or some such thing, and you vary metric as unrestricted as a dynamical variable, then you can show that the gravitational field equations cannot remain invariant. What it means is that if you fix your lambda, you have some beautiful idea as to why lambda LP square should be some 10 to the minus 122, and somebody sneaks and adds the constants to L matter, which he is allowed to do, or if the universe undergoes a phase transition, you are in trouble, because whatever value you have come up with has been completely demolished. So, the real problem is not with cosmology or cosmological constant, but the real problem is with gravity. We have been going around for so many years writing the field equations by varying metric in an action, and this must be wrong because this ignores the most important fact which we know about gravity, namely that through the phase transitions at tree level, the gravity seems to be immune to shifting of the 0 level of the energy density. So, we do not know how to do that yet, but I am going to show you how it can be done. But the basic idea is that this seems to be some experimentally or observationally established fact. So, you would like to do dynamics incorporating that. So, the real cosmological constant problem is actually a gravity problem. The way we do gravity, it goes and couples to this constant, and which it should not. So, what is necessary to solve this problem? The first thing you need to do is to make the field equations invariant under adding a constant to the Lagrangian. Second, you want to, if you do that, the field equations will not care about the cosmological constant, but we do know that we want to find a cosmological constant. So, arrange the matters in such a way that the solution to the field equations, when you do the first integral of that, lambda arises as an integration constant. This is fine. So, you have got equations which are invariant under this, and there is only one lambda which you can fix, because there is only in cosmology there is you integrate this equation only once, and at that time you have to fix that constant, which is your 0 level. Finally, if you want to do this, you need an extra physical principle, because your action principle now does not care about lambda. So, it can never tell you what lambda is. So, you need an extra physical principle to fix its tiny value. What I am going to tell you is that there is a way of looking at gravity as what people usually call the emergent gravity paradigm, and it can take care of 1 and 2. Okay. But the current talk is not mainly on emergent gravity paradigm. I have written and spoken about it in various fora, but I am going to first concentrate on that. But remember that giving you any numerical value for lambda is absurd until I have in the back of the blackboard some way of doing this, which I have, which I will come to in the end. So, I am going to first talk about this part. How do I come up with a physical principle which fixes the lambda value? So, this is the take home message of the 2 talks. I will show you that there is a physical principle by which you can get this relation. This relation essentially connects the 3 densities of our cosmology: the rho lambda, rho inflation, and rho EQ. and if you just quickly put in the numbers and punch your calculator, you will find that this is at the right ballpark figure, and the smallness is explained by minus 36 pi square. So, this is what I want to show you. In particular, I can invert this relation. Observations, cosmological observations are very precise, and it tells me what is rho lambda and rho eq. So, I can invert it and calculate what is rho inflation is. There is a little bit of caveat here. This rho inflation is not the sort of steady rho inflation, but it is the one after the reheating. So, there can be a factor of 10 or so different there, but except for that, it certainly gives you a bound and it gives you a factor of 10 leeway there. But except for that, this relates the three phases of the universe. So, how do I do that? So, let us go back to the diagram, and there are these three phases which is pointed here, and let me take away this AEQ because that is not going to play any significant role. Now, if you think of any given length scales, it will cross this universe at the Hubble radius at 3 points. Now, if you think about it, this is a little bit peculiar. Here are two other kinds of universes which were sort of popular at some stage or the other. So, here is the SCDM, the standard cold dark matter with no cosmological constant, which many people have been pushing for many decades, which involves an inflationary phase which makes omega total equals 1, and eventually it has a matter dominated phase which just goes up and up. So, here the modes sort of cross the Hubble radius here and enter, but they never leave. You can also think of a universe where there was no inflation, but it starts from a Big Bang singularity, and but there was a cosmological constant. So, in that case there are modes which again cross twice, or some modes just go out, and here also there is one mode which is completely inside. But what happens in our real universe is there is a class of modes which behave differently. For example, there is a critical k minus or a wavelength which just skirts here, so that it never enters the Hubble radius because the Hubble radius has just turned around. That happens only because there is a cosmological constant here. Then similarly, there is another mode which is just going to cut here and it is going to stay inside, and we are somewhere here. Okay. Now, the interesting thing about this diagram is that all the length scales in this range, suppose I have some way of counting how many length scales are there, I will make that more precise, that is where my definition comes in. Suppose I count the number of length scales which are here, they all leave the Hubble radius here, they all go through the radiation matter dominated here, and they all leave here. So, there is an interesting conserved quantity, so to speak, which is the number of length scales which cross the Hubble radius in these three phases. Okay. So, this is what I want to latch on to. Well, the first person who actually thought about it is Jorken, and this is a beautiful paper which if you have not seen, you should go and read it up, and I followed it up early on at some stage. What it tells you, I mean, he does not put it in that way, but that is what it amounts to. If you think of Planck scale inflation and pure radiation dominated universe, which is fine because matter domination exists only for some 10 decades out of 10 to the 28. So, and then there is a inflationary phase. It turns out that the universe expands by the same factor through each one of these phases. What is more, in this cosmic parallelogram, this point has some deep significance because the de Sitter universe has a temperature just like black holes have a temperature. And this is the epoch at which the CMB temperature would have cooled down to the de Sitter temperature, and we will be just dominated by vacuum. So, there is some interesting physics here, and what I am trying to argue is that you can count the number of length scales which cross through this, flow through this parallelogram, and that number is a good number for the universe. So, I give it a name, I call it cosmological mode index. And now I have to define it, because how do you define how many length scales are there in a given length? I mean, you can come up with any kind of definition, but there is an interesting way of doing it. Suppose you want to study the number of modes which cross the Hubble radius, which are in the Hubble volume, between two epochs A1 and A2. If you for a moment think of it as some physical wavelength of some scalar field or any field, but you think of take away the spin state so that it is just a single degree of freedom, then the most natural thing we do in statistics is to do the phase volume d3x d3k upon 2 pi the whole cube. This is the number. So, using this you can calculate what is the total number of modes which crosses, or total number of length scales which cross the Hubble radius between two epochs A1 and A2, and you get an expression. So, again is a fairly straightforward computation. Now, I have shown you here, let me just go back for a minute, the number of modes with any given definition which cross here is the same as which cross here, which is same as which cross here. And of course, this part is radiation and matter dominated. So, it is well determined observationally. So, I can calculate what this number is in this phase. It is equal to the other things as well. So, you compute this and it is a measurable single number for our universe. Okay. So, here there is just a definition and you can just count this number and check this. At this stage, there are two ways to proceed. A very conservative approach will be, let us go and measure NC from our data and see whether it looks interesting, and let us try to make sense out of it. There is a more radical route which I want to push here. Do I have an idea as to what this NC should be from some kind of speculative fundamental considerations? And then you can give a value for NC and then go and plug it into this, and that will give you a relation between the cosmological constant and the other constants in the universe. So, I want to follow the second route, and I am going to postulate that this NC is equal to 4 pi, or rather NC upon 4 pi is 1. Now, this essentially comes from some quantum gravitational considerations, that if you take the area of a Planck length sphere and divide by LP square, the number of bits of Planck length on the surface of that sphere is just 4 pi, it is a pure number. So, the idea is that all these modes which are flowing through the cosmic parallelogram had a length scale which is comparable to Planck length very early on, and it is an imprint from that quantum gravity which is coming all the way through. So, this postulate immediately determines the value of lambda LP square, rest is straightforward calculation. So, you do the computation and you get the result which I quoted in the beginning. I mean, it can be written in different ways. So, you cancel out all the LPs, and then this is rho lambda is rho inflation, rho EQ kind of this number. This is a straightforward computation which you can do. There is one caveat about it which I will tell you in a minute. Now, just to get the ballpark figures before we go into details. So, if you think of inflation taking place at some scale, and this is a dimensionless number characterizing that, this corresponds to, I have taken some 1.2 into 10 to the 15 GeV and rho EQ of 0.86, you plug it in and you get the right result. Okay. I am giving the talk only because it gives you the right result. But at this level, there are no free parameters. So, let us pause for a minute and think about this. If you invert this and take this rho EQ and rho lambda, it tells you what is the allowed range for the inflationary scale, and that is typically of the order of 10 to the 15 GeV. And as I said, there is a caveat of reheating, because what this actually measures is the radiation density just after reheating, and that can be different from the actual Hubble constant at the inflationary phase, and that can change things by a factor 10, but this is a lower bound. But just look at the numerology of an expression like this. You have no idea that when you plug in these numbers, you should get anything like 10 to the 15. You could have got 10 to the 10, you could have got 10 to the 12. Okay, if you have got 10 to the 14, you would probably fudge it around, but it could have been 10 to the 8, or it could have been 10 to the 20. Now, I find it rather tantalizing that with such an elementary idea as the number of modes which are crossing this is equal to 4 pi, you get an answer with no free parameters, which is this. The rho inflation, if you give me a precise model of inflation all the way with rho reheating, then I can go and compute this. So, for every model of inflation, now I can predict what this will be, and certain class of inflation models can again be ruled out by this, so to speak. So, this is the same result in graphical form. So, this is the rho lambda divided by the fiducial rho lambda and against rho EQ, and this is the sort of mean value which comes out of this. And you can ask how much variation I have. This is what I mentioned to you. This is the kind of liberal error bars in rho EQ, and this is in rho lambda from observations, and you can bracket it by these two curves, and that is very narrowly defined. It is essentially 1.1 to 1.2, which is the number I quoted for you. So, what are the new features here? The first point is that it gives you a completely unified view of cosmic evolution. I am saying that the inflationary scale and the rho EQ and the rho lambda are not completely independent objects. They are connected by this conserved quantity, okay, which is the cosmin. Second, the whole idea is that there are two eternal de Sitter phases which could have been eternal, and then there is a relevant cosmic parallelogram which comes in between, which I define by these modes, these selected modes, and that is the transient phase, and these three are connected by this, and what is important is the two de Sitter phases, and that is what we are connecting. There is also something interesting which happened. This is more for experts in the audience. People keep talking about modes crossing the Hubble radius, but you can do entire inflation without ever mentioning that string, okay? Because this is just a way of thinking about it. When you look at a differential equation, when wavelength is much bigger than the Hubble radius or wavelength is much smaller than the Hubble radius, the behavior of the equation changes, and is a very nice way to talk. But there is nothing fundamental happens when a mode is crossing the Hubble radius, okay? So, in conventional inflationary physics, it is a nice way of thinking about it, but you could have just integrated that differential equation and got the same results without worrying about what is happening. But here it is slightly different. I can't quantify how it is different, but somehow Hubble radius seems to play a more important role. Keep that in mind, because that will come up again. Now, of course, if you go and if you take the conservative approach and you go and measure the cosmin for the universe, you will find that it is very close to 4 pi. I will not go through this, but essentially it is the same data which is produced in a different way. You do not postulate anything, you just have a pure number which is defined for you, and you compute it from observational data. You will find it is close to 4 pi. It is close to 4 pi up to something like 3 decimal places, third decimal place accuracy for relevant values of the parameters which we know. So, if some number is close to 4 pi to 3 decimal places, maybe it is like what was mentioned earlier, it quacks like 4 pi, it walks like 4 pi, maybe it is 4 pi, and then you should go back and ask why it is 4 pi. So, that is the question, why is this 4 pi? I have not quite figured it out, but I can share with you some of the thoughts which come from the emergent gravity paradigm, but it is probably a lot simpler to understand why a number is 4 pi rather than why a number is 10 to the power minus 123. So, I think there is hope for solving the issue. Okay. So, in order to orient you or rather disorient you from the conventional cosmology, let me ask a few questions which we normally do not ask in cosmology. So, one fundamental question you could ask is, why does the universe expand? Well, Einstein's equation do not give you an answer, because it is invariant under t going to minus t, and I could have had a contracting phase of the universe as well. Of course, if you tell me that the universe is expanding today and you integrate Einstein's equation backwards, it would have been expanding in the past, but that is a question of choice. Second, one of the most peculiar things about the universe which you do not see normally in laboratory systems is that it seems to be the only thing known to us where it started out quantum mechanical and then spontaneously became classical. I mean, if you start a system quantum mechanically, as time goes on, it does not sort of naturally evolve into a classical state. I mean, this can be made more precise in terms of Wigner functions and peaking of trajectories, etc. But it does seem to have done that. And in this paper, I have tried to claim that these two are actually related, but I will not go into that. Then the third point, which I had already talked about, why is gravity immune to the vacuum energy? And there is also this question as to why does our universe in the large scale has a preferred Lorentz frame. So, one of these days Samsung will come up with a gadget 50 years down the line which you carry with you, and it measures the dipole anisotropy of CMB as you are driving, and it will tell you precisely in which direction you are going and with what speed, because you have a preferred Lorentz frame and you are moving with respect to that Lorentz frame, and it can be done. It is just a question of technology which is preventing us from that. So, why does it have that? None of these questions are compelling and they all have standard answers. For example, you will say, oh, whoever said that the symmetry of the equation should be maintained in the symmetry of solutions. In fact, most often it does not. So, of course, Einstein's equations are generally covariant, let alone Lorentz invariant. You choose a particular solution which sort of has a preferred problem. So, what is the big deal? So, all of them can be answered in the conventional cosmology, but maybe it is also possible that this will persuade you to think that cosmology is not probably part of a general relativity, that you should think of cosmology as an independent existence and try to understand that. This kind of viewpoint comes up quite a bit in the so-called emergent gravity paradigm, where you want to think of gravity as emergent. So, I will sort of introduce you into that, and I will tag on to a couple of features in emergent gravity paradigm, which is relevant to this cosmological constant problem. Because I already told you that in emergent gravity paradigm, gravity does not couple to the 0 point energy. Okay, so this is the conventional point of view. You think of gravity as a fundamental interaction, and there are some special solutions in which you will have space-time thermodynamics, etc. So, the new perspective is to turn it upside down and say that the space-time thermodynamics and the microscopic degrees of freedom underlying that is more fundamental, and the gravity is an emergent phenomenon. It is something like the statistical mechanics of atoms of space-time, and you take the thermodynamic limit of that. So, the main point about this paradigm, which has been around for quite some time, is that there are several results in that which keep coming up, which suggests that the classical gravity has the same conceptual status as elasticity or hydrodynamics. Okay. So, in fact, if you have elasticity and you look at the lattice vibrations of a solid, and if you quantize it, you will get phonons. So, similarly, if you take Einstein's equations and you do linear perturbation theory and you quantize it, you will get gravitons. But phonons do not tell you what is the quantum structure of matter is, and in any more than gravitons will tell you what is the quantum structure of space-time is. There can be a deeper layer there. So, one way to do this would be to study the space-time dynamics exactly the way people studied fluids, and they made tremendous progress without knowing atomic structure of man. And this leads to several new insights about both gravity and microscopic structure. And one of the key points is that this connection transcends Einstein's general relativity, but I am only going to stick with Einstein's general relativity here. Many people have worked on it, but I am essentially going to summarize the work done in my group. Okay. So, the first point, which I will elaborate a little bit more, but not much more, is that in here you derive gravitational field equation not by varying the metric in an action, but from a thermodynamic variational principle. You essentially maximize enthalpy of the null surfaces, and you get the Einstein's equation almost. What you get is equivalent to what happens in unimodular gravity, that is, you get the trace free part of the Einstein's action, and the cosmological constant arises as an integration constant in that, and you need a new principle to fix its value, and I have already told you what that principle is. It is cosmin is equal to 4 pi. There is something more remarkable which happens. In this picture, the entire Einstein's equation, after you have got the Einstein's equation with a cosmological constant or whatever, can be understood in a very different way as some kind of a quest towards holographic equipartition. That is, in any region you define degrees of freedom on a surface, and you define degrees of freedom in the bulk, and you can show that they are equal in any static space-time. And then you can show that the evolution equations, they are essentially driven by the difference between this n surface and n bulk. And it also gives an alternate perspective to cosmic expansion. So, let me tell you where it comes from. So, if you want to study thermodynamic approach to gravity, you need the thermodynamic quantities, you need temperature, and you need entropy. So, one of the, in fact, I would think it is the most beautiful result in combining quantum theory and gravity, is that if you have a class of observers who perceive a horizon, then they will attribute a temperature to that horizon which is related to the acceleration, either the surface gravity or the acceleration of the observer. This was derived by Paul Davies and Bill Untrue. And many cases which you know are just special cases of this effect or can be thought of like that. And this temperature is completely independent of the field equations of gravity. This is just an effect in the given curved spacetime. So, what it tells you is that at any given point, if you go to a local inertial frame with a freely falling observer, there is a region in which the freely falling frame is valid, and you can also have an observer who is sitting quietly there, and he will have a trajectory like this, which is approximately hyperbolic. If you set up a quantum field theory with vacuum fluctuations here, they will look like thermal fluctuations to this observer. It is a very, very non-trivial equivalence, and it actually makes thermodynamics observer dependent. This is as far as temperature is concerned. So, you can introduce temperature into the space time in terms of these local Rundler observers, that is what they are called. What about entropy? Well, there is this old John Wheeler-Bekenstein dialogue that if you have a horizon and you have a hot cup of tea and you plunge it into the horizon how do I save second law of thermodynamics? The conventional answer is that when you throw this in, the area of the horizon increases and you have to attribute some entropy to the area of the horizon, and as a result of which everything is fine. But you do not have to plunge the T into the horizon, you can plunge the horizon onto the T. That is, horizon is a null surface and you can think of a virtual displacement of the null surface, and the same thing should happen if you manage to do that, which in turn means that there must be an entropic cost to displacements of null surfaces. So, null surfaces come with its own entropy if you try to perturb them, and you can associate, once you have entropy, you can associate all kinds of thermodynamic quantities with that. So, you have a null surface and you perturb it slightly, and then there is some kind of a thermodynamic potential attached to that, which to the lowest order will be quadratic in the derivatives and L square. So, you have a temperature and you have an entropy associated with it. So, you can ask what the maximization principle is. There a nice thermodynamic maximization principle which will get you the field equation? Indeed, it does, and you will find details in this paper. It turns out that it is nicer to do this in terms of a couple of different variables than what you usually use. This is the metric tensor, and you can define root minus g times GAB as the coordinates, and then there is a corresponding canonical momenta which is like this. You do not have to think of it as canonical momenta, just think of these two as definitions as indicated by this. Then your variational principle is essentially this: you take any null surface and you compute this quantity where there is a Lie derivative with respect to the null congruence on the surface, and you add a covariantly conserved energy momentum tensor by this, and then you go and maximize it for all the null surfaces. So, you say that the entire space time has entropic content in the null surfaces, and in fact, one can show, which is there in this paper, that this is somewhat like the enthalpy density T times S when you integrate over the volume, the enthalpy density of this null surface, and this again for an ideal field fluid, for example, will be rho plus P, which is the Ts of matter. So, you are adding the total enthalpy of the null surface, and there are equivalent formulation in terms of pure entropy, pure free energy, etc., because once you know you have to extremize one, you can extremize anything else. If you do this and you crank through the algebra, you end up getting a field equations which is this. What it tells you is the Einstein's equation projected onto the null vectors should be 0 for all null vectors, and it is a elementary exercise using Bianchi identity and conservation of TAB. So, you might panic for a moment that everything which is proportional to GAB and here will go away, but it will resurface when you use the Bianchi equations and Bianchi identities, and you end up getting this with an arbitrary constant lambda. So, in this particular approach, you recover Einstein's equation, but the status of lambda is very different. It is an integration constant, and this action which I am talking about is manifestly invariant under TAB going to a constant times GAB, because LALB is null and that just kills it. So, any 0 point energy, any vacuum fluctuations, etc., just does not care about gravity, in the sense that it does not care about the entropy of the gravity. Now, I said that you can vary this and get Einstein's equation, but that is a little bit silly, right? If I am starting with a thermodynamic approach to gravity, then I should be able to interpret Einstein's equation itself in a thermodynamic way. In fact, capital GAB is equal to kappa TAB has no simple physical interpretation at all. Now, I will show you how a much nicer interpretation arises. To do that, let us look at space at some constant time, and let us look at static space time, for which there is a well defined notion of equipotential. I mean, there is essentially G naught naught equals constant surface. So, let us consider this surface, and let us associate with the area the number of degrees of freedom, which is area upon LP square. This is what I tuned you in earlier on, that you put patches of Planck length on the surface, and you think of number of degrees of freedom on the surface as the area of the surface divided by LP square. You have a normal, and there is a acceleration due to gravity, and you have observers sitting on this equipotential surface, and there are observers who are freely falling at every point. So, you take the vacuum state of the freely falling observers and you associate with respect to the local Rindler observers a temperature which is G local over upon 2 pi. You can also then compute an average temperature for the surface, which is this. So, think of this surface, I mean if it is a nice spherical surface in some black hole spacetime or something, it will be a constant, but think of in general as the average temperature as the temperature of this surface, and there is matter inside. If the matter is in equipartition with this temperature, which it need not be, but if the matter is in equipartition with temperature, then the number of degrees of freedom of that bulk matter will be that into half kT should be equal to the energy contained in that. Okay. So, this allows you to define a notion of n bulk, you have defined a notion of n sulfur. The amazing result is that if Einstein's equation hold and the spacetime is a static spacetime, n surface is equal to n bulk. This is a rigorous result. For any static spacetime, you can prove this. So, in some sense you say that all Einstein's theory tells you for static spacetimes is that they are in holographic equipartition. In fact, you can reverse the logic. In static spacetimes, if holographic equipartition has to hold for every surface, then it is equivalent to Einstein's equation. For those of you who do not do general relativity, let me this is just for fun, let me just do a Newtonian example like this. What it tells you is that n surface is equal to n bulk, which is written like this, which you can change into the energy is being given by half kT times area upon Lp square. Area upon Lp square is n, it is half n kT. Okay. So, now what you do is that write energy as energy density times volume and substitute for this temperature G over 2 pi, and G, that because it is equipotential surface, this is G dot n, and you have a surface integral of a dot product of a vector, which is equal to the volume integral of divergence of G, and lo and behold you get divergence of G is equal to this quantity, which is just Poisson's equation. So, this is some kind of a Gauss law giving you holography in Newtonian limit, but everything I said here has a natural generalization to general relativity. But what makes this spacetime evolve? I just took static spacetime and told you this happens. You play the same game here, then you can show another very interesting result. You can show that this particular quantity, which is like rate of change of momentum with some indices contracted in a suitable way, the rate of change of momentum integrated over this region is given by essentially n surface minus n bulk. This equation is identical to Einstein's equation, it implies and implied by Einstein's equation. So, this is the reformulation of general theory of relativity. You can think of general theory of relativity, the dynamical equations of general theory of relativity, capital JV equals kappa TAB, which is 10 equations, as equivalent to the validity of this equation for every potential equipotential surface or its generalization, because in a dynamic situation you have to be more careful with that. And it is the difference between n surface and n bulk which drives the evolution of the geometry. When n surface is equal to n bulk, this term will go to 0. Okay. So, this you will find the details there. Okay. Now, I want to come back to cosmology and to the cosmological constant and ask what all these means for that. So, for that I want to first introduce a little bit more detail about the de Sitter spacetime, which has already appeared twice, and in particular I am looking at the de Sitter spacetime at late times, which one natural way of writing it is with an exponential expansion. This is very symmetric and it is very natural spacetime for a kind of an equilibrium state of the thing, and it has a single length scale, and in particular it is time translation invariant. I mean, even though there is a time dependence, if you change t to t plus epsilon, that can be rescaled into this. Okay. And this was the original motivation for steady state cosmology, which is philosophically so beautiful. It is just that nature didn't make use of it. So, this means universe looks the same at all times. Now, you can also, because it is time independent, there must exist another coordinate system which makes it manifest. It is true, you can write de Sitter spacetime in this form, where this velocity is nothing but the Hubble velocity of a observer at origin, so to speak. And if you are looking at black hole spacetime, this would have been the escape velocity. So, it is very similar to the black hole spacetime, except that the velocity has to be changed. And just as black hole spacetimes have a temperature, which I am sure all of you have heard of, de Sitter spacetime also has a temperature, and that temperature is given by this. There is one place where two different H's sit together peacefully. So, you have a temperature associated with this de Sitter spacetime, and now I can play my game of holographic equipartition. So, for a universe, let us take a Hubble radius H inverse and then define this n surface, and you define your n bulk, and then you can go, this E is the Komar, so called Komar energy, which is rho plus 3 p, and so its magnitude, this n we want to be positive, so I put it as minus E over half k T. Then you say that it should maintain holographic equipartition. So, you do not assume Einstein's equation here, you start with this metric, you do quantum field theory in curved spacetime to get the temperature, and then you define these quantities and you demand that this should be there. This is of course equivalent to just standard de Sitter equation. So, you get back the de Sitter spacetime from this. I mean, I have told you that these results go back and forth, so this is just a special case of that. So, pure de Sitter universe maintains holographic equipartition with a constant value for the V does not change. So, it looks very natural to again ask that it is the holographic discrepancy which actually drives the expansion of the universe itself. I mean, this is slightly different from the equation which I gave you before, but it is related to it. There I gave you some canonical momentum and how it changes, but you can translate in the case of Friedman universes to a simpler thing. But now, you just introduce this as a postulate. You say that the volume of the universe inside the Hubble radius is changing dV by dt because of n surface minus n bulk. Ignore this epsilon for a minute, n surface minus n bulk, and by dimension dV by dt should have just a length square, put LP square here. Okay. So, if you are looking at it in dimensionless unit, dV by dt is just n minus n bulk. So, this at this stage I am just postulating. So, this is the volume, this is the n surf, and this is the n bulk. This epsilon is just to take care of the fact that your n bulk remains positive when the energies have switching sign. What is remarkable is that this equation with no free parameter, I do not have to say LP square upon 13 or something like that, with just the natural GH cross upon psi cube sitting there, is identical to the standard FRW dynamics. So, the entire Friedman dynamics of the expansion of the universe can be thought of without using GR by saying that the Hubble volume is expanding in order to, because of the difference between n surface and n bulk, and when n surface is equal to n bulk, it will just sort of have a constant volume of expansion. So, these ideas, so there are two ideas which I have introduced from emergent gravity paradigm is what motivated me to postulate that Cosmin should be equal to 4 pi. So, the first idea is that in emergent gravity paradigm, gravity does not couple to the 0 point energy. Therefore, it is a natural context to solve the cosmological constant problem, and you only need an extra principle to determine what that is. The second idea is that the entire gravitational dynamics is no longer thought of as the dynamical evolution of the gravitational field or any such thing, but it is an interplay between the bulk degrees of freedom and surface degrees of freedom. So, they should play a very key role. So, if you generate this back into quantum gravitational regime, for example, you can think of a discrete version in Planck units. So, you think of time steps in Planck time, and the volume of the universe at n plus 1 step is the volume of the universe at n step plus this addition. Okay. This has implications for example, quantum cosmology. And if you push it further, you will essentially end up saying that at the Planck scales, you would find the number of degrees of freedom or n surface should be equal to 4 pi, which essentially comes from the fact that 4 pi LP square upon LP square is 4 pi. So, with this idea, the whole thing ties together. So, let me just summarize what I have been trying to say. The proper way to think of gravity should be to endow spacetime with thermodynamic properties, just as the proper way to study a solid when you do not know what is its microstructure is to use thermodynamics. You can derive the dynamics from a phenomenological extremum principle, just as you would have done it in fluid mechanics or in elasticity without ever knowing what the fundamental constituents are. And when you do that, you get as a bonus that the field equations are immune to the bulk energy density. This approach has the ingredients to solve the cosmological constant problem the way I have said, because it does not care about the bulk energy density, and you need an extra principle, and it appears as a integration constant. So, you just need an extra principle to fix its value. So, that I have given you an idea that the value of the cosmological constant can be addressed with defining this cosmin, which is the total number of length scales which are crossing the Hubble radius, and a postulate for that, which is 4 pi, which I try to sort of give you a qualitative argument as to at least how I was led to that, but that need to be made more precise. It is interesting that there is a concept of cosmic parallelogram, and as I said, Jorken is the one to introduce that first, but he did not talk about a conserved value, but there is a conserved value of the total number of length scales which is going through that, and that provides a very unified description of the cosmology relating the 3 constants, the rho lambda, rho eq, and the rho inflation. So, you have a crosstalk between this through this quantity which is connecting them. It is like if you have a dynamical system and you calculate kinetic energy and potential energy at one time and kinetic energy plus potential energy at another time, they are linked to each other because the energy is conserved. So, these things can be individually varying, but there is a conserved description. And it, as I said, it resonates very well with the idea that the expansion itself should be thought of as some kind of a quest for holographic equipartition, and it connects quantum gravity, high energy physics, and the cosmological constant, which was of course the original motivation for the whole thing. Thank you very much.